In this video, we're going to look at amides. These are the least reactive of all carbonyl groups. Let's just first look at a classification scheme here. We're going to classify amides based on how many hydrogens remain at nitrogen. A primary amide will have just the acyl group here and 2 hydrogens. A secondary amide will have the acyl group and 1 hydrogen and an R group. And a tertiary amide, again, will have the acyl and no hydrogens on nitrogen. Okay, if we look at the primary and secondary amides, these can be hydrogen bond donors or hydrogen bond acceptors because of the fact that they have a hydrogen at nitrogen, whereas the tertiary amide can only function as a hydrogen bond acceptor. In amides, we have this very strong resonance interaction. It's much stronger than similar resonance interaction depicted in esters and acid chlorides and anhydrides. Okay? This is because the nitrogen lone pair is a lot more basic than the oxygen lone pair. All right? As a result of the prominence of this resonance structure, we have very strong dipole moments due to these resonance interactions. Okay? And we see that reflected in the boiling points here. Notice how this tertiary amide and this secondary amide both have similar molecular weights to ethyl acetate over here on the far right, but look at how much higher boiling these amides are. The one that has hydrogen bonding donor and acceptor is much higher boiling, but we see that both of these amides are much higher boiling than the analogous ester. Okay? Let's see. If you look at a hydrogen at the nitrogen of an amide, it's slightly acidic. The pKa is very comparable to water. It's about 16. This is much lower than the pKa of the corresponding free amine, which is 33. Okay, so let's just imagine we treat this with base. Okay, we're going to make the anion. It's going to have 2 lone pairs at nitrogen. We can delocalize the negative charge at oxygen through that type of resonance interaction. That's quite stabilizing. It's totally analogous to the resonance interaction we saw in carboxylic acids and carboxylate anions. Okay? The oxygen lone pair, or the carbonyl oxygen of an amide, tends to be an extremely good hydrogen bond acceptor because it's got a little bit of basicity associated with it. Okay? So there's more negative charge character at the amide oxygen than there is at the ester or ketone or aldehyde or carboxylic acid oxidation or oxygen. Okay, so we see that when we compare water solubility, we see that these 2 amides here are completely water soluble, whereas ethyl acetate is hardly water soluble at all. Okay, this is something we're going to cover in the next chapter, but we may need to allude to it in a couple of cases here. Amines are basic. Amides are only very weakly basic. Okay. And this is because the lone pair at nitrogen is busy doing this resonance interaction that we see over here. Okay, let's look at how we make amides. For the most part, we've covered all the methods already. The best way to make amides is to take more reactive carboxylic acid derivatives like acid chlorides, anhydrides, or esters, and just treat them with amines. And this leads to the corresponding amide. Another way that amides can be made is by making a salt from a carboxylic acid and an amine. This gives you the ammonium carboxylate, which if heated to a very high temperature will expel water and make the amide. This is kind of more of an industrial scale amide synthesis. You don't see amides like this made in the laboratory usually because the conditions are a little bit harsh. Okay, the only real reactions that we're going to look at in this chapter are amide hydrolysis. We will look at some other amide reactions in the amine chapter because we're going to find that some of the other reactions actually lead to amines. Okay, all right, so we can hydrolyze an amide into its component carboxylic acid and amine components through either strong acid or strong base. Okay, and the acid or base that we need to hydrolyze the amide has to be a lot stronger than the acid or base required to hydrolyze an ester. And this is because the amide carbonyl is so highly stabilized by resonance that it's reluctant to react with any sort of nucleophile. Okay, in the acid-catalyzed amide hydrolysis, we make a carboxylic acid and an ammonium salt, and if we want to get the free amine out, we have to add base later to turn the ammonium salt back into the free amine. Okay, the base-catalyzed ester hydrolysis produces a carboxylate anion and an amine, and if we want to isolate the carboxylic acid, we have to acidify the solution to turn the carboxylate salt back into the carboxylic acid. Okay, so it requires higher concentrations of acid or base, and it requires much higher temperatures to do the hydrolysis. All right, let's look at the mechanism for acid-catalyzed hydrolysis. Notice how we're doing this reaction here pretty much at reflux. A common type of biological molecule, a protein, is also an amide, and it's turned into its component amino acids by a similar hydrolysis procedure. So sometimes you'll see this set of conditions referred to as digestion. Okay. All right, so this is actually the preferred way to hydrolyze an amide. What happens here is that we're protonating the carbonyl oxygen. Okay, we get the protonated amide. This now reacts with water to give us the tetrahedral intermediate. Okay, we lose the extra hydrogen to get this tetrahedral intermediate, and the acid is now going to protonate the amide, and this makes this tetrahedral intermediate here, which is the only one that really has the nitrogen in a form where it can serve as a leaving group. So this set of arrows ejects the nitrogen, and we end up with the protonated carboxylic acid that you see here, and we're just going to do a pretty much irreversible acid-base reaction that turns this into the carboxylic acid and the ammonium salt. Okay, the difficult step here is really this one right here. Okay, the carbonyl group is so stabilized that it's hard to get anything to add at that point. But once that's done, it's relatively downhill from there. Okay, let's look at the base-catalyzed amide hydrolysis. All right, in the base-catalyzed amide hydrolysis, this requires incredibly harsh conditions. This is not the right way to hydrolyze an amide. And I always say there's no way to write a mechanism for base-catalyzed amide hydrolysis without drawing one step that you're not particularly proud of. Okay, so here's what happens. The hydroxide ion is going to attack the amide carbonyl, and this is the hardest step of the reaction, the very first step of the reaction right here. Okay, and this is because the carbonyl is comparatively unreactive relative to all the carbonyl groups that you've seen before. All right, this gives us our first tetrahedral intermediate. It's tempting to just expel the amide like this, but you can't. This is too basic. Okay, so this is a high energy pathway. So it's tempting to do that, but that's not the right way to go, because remember that the amines themselves have pKa's of around like 34 or something like that. So this anion here is just way too basic to just simply generate from an alkoxide like that. All right, so that's not how we do it. Instead, we have to do some things with water. We're going to add water and get a neutral compound. And this is a step that's not particularly favorable. Somehow or another, under very strongly basic conditions, we have to protonate the nitrogen. It's not going to be all that favorable, but to some small extent it can happen. And once this has happened, we can now eject the amine like so. This gives us the carboxylic acid and the amine. In the strongly basic conditions, the carboxylic acid is going to go to the carboxylate salt, and we're going to get the free amine. And if you want the carboxylic acid, again, you have to adjust the pH to something like about 4, where the carboxylic acid would be protonated. Okay, let's look at some equations here. Try and complete these reaction equations. Okay. All right, so the first one up there is an ester hydrolysis. We're just going to hydrolyze right here, break that carbon-nitrogen bond, and we're going to break this into its component carboxylic acid and amine. We're going to assume in these reactions that appropriate pH adjustments have occurred to give us neutral compounds. Okay, this is a type of amide. This is known as a lactam, or a cyclic amide. Okay, so when we hydrolyze the amide, there's still going to be a linkage between the carbonyl oxygen and the nitrogen, right? We have these 4 CH2 groups linking the carbonyl oxygen and the nitrogen, as well as the direct carbon-nitrogen bond of the amide group. Okay, so when we hydrolyze this one, we're going to generate a compound that has both a carboxylic acid and amine functionality. Okay, we're going to talk about this in the amino acid chapter, but it's pretty much an irreversible process, the self-neutralization that's going to occur when you have a carboxylic acid and an amine as part of the same molecule. All right, so this question here is a retrosynthesis. Okay, so this looks like the conditions for an amide hydrolysis. And we have an amine and a carboxylic acid. So that means the product over there on the left side of the equation should have been a amide. Okay, so this is the amide that would correspond to those two hydrolysis products. Okay, here we have in this last one an amino alcohol, and what we see is KOH in heat. It's hard to tell whether this is an ester hydrolysis or an amide hydrolysis. Okay, so the examiner who wrote the question wants us to write 2 answers. So the 2 answers we're going to write are either the ester or the amide that corresponds to that amino alcohol. Okay, so either of these compounds here would transform to the amino alcohol and cyclopropane carboxylic acid if you treated it with KOH and heat. Again, both the ester or the amide would hydrolyze. The amide would be harder, but we don't see like the temperature or the concentration of base specified in either of these. Okay, so I think this is where we're going to end this one. This is going to be a relatively short video here. It's all totally focused on amides. The rest of the carboxylic acid derivative chapter is going to be concerned with nitriles, and then a hodgepodge of spectroscopy and less common groups like nitrogens with 2 acyl groups on it and things like that. So we'll leave that to the fourth video, trying to keep all the videos of reasonable sizes.